What we really wanted to achieve here is like, well, why make this really fast car that an electric car is the best car?
In an industry already charged with innovation, Elon Musk has just dropped another bombshell with Tesla's new condensed super battery that comes with only a 15-minute charging time. With promises of faster charging, ultra-high energy density, and driving ranges approaching 1,000 kilometers, this battery doesn't just raise the bar, it hurls it into a different stratosphere. What makes this moment even more compelling is the timing. As Chinese giants like CATL and BYD dominate the EV battery space with scale and affordability, Musk steps forward not just to compete, but to transform. Let's dive straight in. Tesla's battery evolution. When Tesla was founded in 2003 by engineers Martin Eberhard and Mark Tarpenning, and later transformed under the leadership of Elon Musk, it faced a hostile automotive landscape. At the time, electric vehicles were largely dismissed as impractical novelties, limited by sluggish performance, short range, and prohibitively expensive batteries. The global auto industry was entrenched in the internal combustion engine, and even early hybrids like the Toyota Prius were viewed with skepticism in some markets. But Tesla saw something else. The key to making EVs mainstream wasn't just in sleek car design, but in breaking through the limitations of battery technology. From the outset, Tesla focused heavily on batteries, treating them not as off-the-shelf components but as the very heart of its vehicles. The company's first production car, the Roadster, was built on the chassis of a Lotus Elise but packed with over 6,800 lithium-ion 18,650 cylindrical cells, the same type commonly used in laptops. Manufactured by Panasonic, these 18,650 cells were repurposed and repackaged by Tesla engineers into a novel battery pack configuration. This move was radical. No major automaker had used consumer-grade lithium-ion cells on such a scale in a road vehicle. Yet this allowed Tesla to bypass traditional battery suppliers and deliver the Roadster with a then unheard-of range of over 200 miles, around 320 kilometers, per charge, something no EV had achieved at the time. But Tesla wanted more. The EV manufacturer deepened its collaboration with Panasonic and laid plans for something unprecedented in the auto industry, a vertically integrated battery manufacturing facility. In 2014, Tesla announced the Gigafactory near Sparks, Nevada. By the time its first phase opened in 2016, the facility was the world's largest building by footprint. The idea was not only to produce battery packs in-house but also to streamline the supply chain, cut down manufacturing costs per kilowatt-hour, and scale EV production to meet global demand. This move paid off. Tesla's second major cell innovation came with the Model 3, launched in 2017. Here, Tesla shifted from the older 18,650 cells to the more advanced 2170 format, a cylindrical cell measuring 21 mm in diameter and 70 mm in length, developed jointly with Panasonic at the Gigafactory. These 2170 cells were a technical leap forward, offering higher energy density, better thermal management, and improved longevity compared to the 18,650 batteries. They enabled Tesla to offer longer-range vehicles at more competitive prices, cementing the Model 3 as the best-selling EV globally in subsequent years. But the biggest leap in Tesla's battery roadmap came during its much-anticipated Battery Day on September 22, 2020. It was here that Elon Musk and Tesla SVP Drew Baglino unveiled the 4680 tablet cell, a revolutionary design that marked a sharp departure from previous formats. At 46 mm in diameter and 80 mm in length, the 4680 offered 5 times the energy, 6 times the power, and a 16% increase in range compared to the 2170. More importantly, its tabless design, eliminating the internal tabs connecting the electrodes, reduced resistance and allowed for faster charge and discharge cycles while simplifying manufacturing. Tesla also introduced structural battery packs, where the 4,680 cells would become part of the vehicle's chassis itself, improving rigidity and reducing overall mass. The manufacturing improvements tied to the 4680 included Tesla's new dry electrode coating process, acquired through its 2019 purchase of Maxwell Technologies. This technique eliminated the need for wet solvents in electrode production, cutting both cost and environmental impact. Since 2021, limited volumes of the 4,680 cells have been produced at Tesla's pilot line in Fremont, California, and later scaled to Giga Texas near Austin. These cells now power select versions of the Model Y and Cybertruck. But it was clear this was a transitional phase leading towards something even more ambitious. That ambition materialized in 2025 with the reveal of Tesla's condensed battery, the culmination of 2 decades of research, thousands of patents, and multiple manufacturing revolutions. Though details were tightly held prior to launch, the condensed battery represents a shift from lithium-ion to a new solid-state adjacent chemistry incorporating silicon nanowire anodes and high-nickel cathodes. This leap has resulted in significantly higher volumetric and gravimetric energy density, estimated at over 450 watt-hours per kilogram compared to around 250 watt-hours per kilogram for the 2,170 cells. The result is a longer range, faster charging, and drastically lower thermal risk. What is Tesla's condensed battery? Tesla's condensed battery is the next leap in energy storage, designed to redefine the metrics of performance, efficiency, and safety in electric power systems. Officially revealed in 2025, the condensed battery is the culmination of over 15 years of Tesla's vertical integration in battery research, from cell architecture to raw material processing. Unlike traditional lithium-ion batteries, this system packs significantly more energy into a smaller footprint, while also offering advancements in durability, charging speed, and environmental sustainability. At the heart of this new system is its unparalleled energy density. Tesla's condensed battery exceeds 450 watt-hours per kilogram, a notable increase from the 250 to 270 watt-hours per kilogram achieved in the 2,170 cells used in the Model 3 and Model Y, and the roughly 300 to 330 watt-hours per kilogram achieved by the newer 4,680 cells powering select versions of the Cybertruck and Model Y. The leap in energy density means that vehicles equipped with these batteries can achieve longer driving ranges, potentially over 800 kilometers or 500 miles per charge, without increasing the physical size or weight of the battery pack. This makes the battery ideal not just for automotive applications, but also for drones, aircraft, and portable power systems where space and weight are critical. One of the most transformative elements in the condensed battery is the use of silicon nanowire anodes instead of traditional graphite. Silicon has long been considered a superior anode material due to its ability to store up to 10 times more lithium ions per gram than graphite. However, the major drawback had always been expansion. Silicon swells up to 300% during charge cycles, causing degradation and reducing battery lifespan. Tesla, building on research from acquired companies like Maxwell Technologies and collaborating with research teams in Texas and California, developed a nanostructured silicon architecture that mitigates this swelling. These ultra-thin nanowires allow lithium ions to flow more efficiently while maintaining structural integrity, leading to both higher capacity and better cycle life. Complementing the silicon anode is a solid-state electrolyte, replacing the liquid electrolyte used in conventional lithium-ion cells. Solid-state electrolytes, typically made from ceramics, sulfides, or polymers, offer significant safety improvements. They are non-flammable and eliminate the risk of leakage, overheating, or explosion caused by dendrite formation or thermal runaway. Tesla's electrolyte blend is believed to be derived from lithium phosphorus oxynitride or LiPo with proprietary stabilizers, enabling high ionic conductivity and stability across wide temperature ranges. The result is a battery that can withstand extreme thermal and mechanical stress, opening doors for aerospace and military applications. On the cathode side, Tesla has opted for a high-nickel, low-cobalt composition, a shift that began with the 2170 and 4680 cells but is now refined to new levels. Traditional NCA or nickel-cobalt aluminum cathodes typically contain 80% nickel, but the condensed battery's formulation pushes this to 88 to 90%, drastically reducing cobalt content, which is expensive, ethically controversial, and environmentally damaging to extract. This change not only improves energy density but also aligns with Tesla's broader supply chain goals, reducing reliance on cobalt mining in the Democratic Republic of the Congo and increasing use of North American and Australian nickel sources. What truly sets the condensed battery apart is its cross-sectoral versatility. While Tesla's EVs are the primary deployment target, the company has designed this battery to be modular and scalable. In 2024, Tesla's energy division began testing condensed battery modules in its Megapack systems at the Moss Landing Energy Storage Facility in California. The results showed a 38% increase in power output and a 25% decrease in thermal management costs compared to traditional LFP-based packs. Elon Musk has also hinted at applications in Tesla's Optimus humanoid robots and SpaceX's Starship systems, where high-density energy is essential and space is at a premium. Another key factor in Tesla's condensed battery is the manufacturing ecosystem surrounding it. Tesla's battery materials refinery in Corpus Christi, Texas, which became operational in early 2024, supplies key inputs like battery-grade lithium and nickel. This facility supports Tesla's strategy of vertical integration, reducing dependence on external suppliers and minimizing geopolitical risks. In tandem, Giga Nevada and Giga Texas are scaling up pilot lines dedicated to condensed battery production using Tesla's dry electrode coating and advanced thermal compression bonding, which reduces water usage and simplifies cell assembly. The unveiling of the condensed battery in 2025 marks a new era in energy systems, but Tesla has made clear that this is not the final form of EV innovation. With enhanced performance, recharge times under 15 minutes for a full charge, and dramatically lower fire risk, the condensed battery has the potential to accelerate the mass adoption of electric vehicles, autonomous systems, and distributed energy grids.